If you have looked at my previous video on the vector equation of a line in 2 dimensions, and therefore in a plane, then you'll see how the same ideas and concepts apply in 3D space. In this video, I will focus on some exercises in 3D space using what we learned in 2D, as well as using the traditional notations for equations of lines. In a previous video, we have seen that the vector equation of a line in 2 dimensions can be written as such, where we have a general position vector which tells us the coordinates of any point on our line, so a general point. And furthermore, we have a position vector which relates to a specific point for which we know its coordinates. So the difference between B and A is that B represents a general point for which we try to find its coordinates, whereas A represents a specific point for which we know its coordinates. And finally, we have our direction vector multiplied by scalar, and the direction vector gives the direction of our line. However, in 3D, I will be using a different notation, a traditional notation that we use for vector equations of a line, which I alluded to in another video for the Cartesian equation of a line in 2 dimensions. So instead of having a position vector B, I will have a position vector R, which represents the same thing. Moreover, the traditional notation favors lowercase letters. So instead of a capital position vector A, so capital A, I will have a lowercase a. And instead of having a parameter, so a scalar k, I'll be having a scalar t, the parameter t. And the reason why I have a parameter t instead of a k is that in 3 dimensions, we have the unit vector k. And therefore, to avoid all confusion, I will have a parameter t instead. The only key difference between the vector equation of a line in 3D compared to 2 dimensions is that for position vectors, instead of them having 2 coordinates, they have 3 coordinates. What I mean by this is, since we're not working on a plane but in 3D space, when we have a position vector r, which I will draw right here, when we have a position vector r, we need to decompose it into the x, y, z axes using the unit vectors I hat, j hat, and k hat. Therefore, our position vector r will be written in the form x in the I hat direction plus y in the j hat direction plus z in the k hat direction. So that's our general expression for a position vector r in our Cartesian frame. Or we can write it as such, x, y, z in coordinate form. When our position vector is written in this form, it is implied that x is the coordinate in the I hat direction, y in the j hat direction, and z in the k hat direction. Essentially, that is the only difference when we're working in 3 dimensions. Instead of having 2 coordinates, we have 3 coordinates. And you'll see in a later video for the Cartesian equation of a line in 3D that it changes the form of the equation, but the foundations behind the equation of a line stay the same. So we have the tools to find the vector equation of a line in 3 dimensions. So now let's solve some problems. In this question, we want to find the vector equation of a line in terms of the parameter t. And what we are given is a point which lies on our line. And in this case, it's the point 2, 0, negative 1. And what does this mean? This means that we have a specific point which lies on our line, and we know its coordinates. And therefore, it corresponds to the position vector A written out here. Because we know that we can associate any point with the vector which has the same coordinates as that point. And therefore, we have our position vector A, which in vector form can be written out as 2 in the I hat direction plus 0 in the j hat direction. I'll write it down here, but we don't need to write it in general. Minus k, so minus 1 times the unit vector k. Additionally, we are given the coordinates of a vector that is parallel to our line. And fundamentally, a vector that is parallel to the line also gives the direction. And therefore, any vector that is parallel to our line is a direction vector to our line. And we can have many direction vectors. They can be expressed in different coordinates as long as they give the direction of our line or they are parallel, which is equivalent. In other words, our vector u here, our direction vector u, in this case, is minus 3I plus j minus k. Now, using the vector equation of our line, we can solve our problem because r can be written as a plus tu, and a, we already know its coordinates. Ultimately, we obtain an expression for k, which is given by a, first of all, added with our direction vector u multiplied by the scalar, or equivalently the parameter t. Since u is given by this expression over here, tu will be given by the expression t times the coordinates of our vector u, and therefore the expression for tu will be t times the individual components. Ultimately, we get the vector equation of our line over here, where this part represents our specific point A, which is written out by the position vector A, and this is our direction vector u. Equivalently, we can write our vector equation of our line by factoring out each individual components, so the unit vectors. So for example, here in the I hat direction, I have 2, but I also have minus 3 that is multiplied by t, and therefore it features in this vector equation as 2 minus 3t. Similarly for j, we have 0 plus 1 times t, and so we have tj. And finally we have minus 1k plus minus 1 times t in the k hat direction. So we just factor out the unit vectors. So thank you for watching this video. Hopefully you liked it. Hopefully you learned from it. And leave a comment down below if you have any questions, of course. And don't forget to leave a like and subscribe to my channel or share my videos.